All right, well, hello everyone. I am Christian Schulz from the University of Illinois Urbana-Champaign. My co-author is Philipp Hieronymi from the University of Bonn, and our paper is a strong version of Cobham's theorem. So, if we're going to talk about a strong version of Cobham's theorem, we should talk about the original Cobham's theorem. A couple of introductory definitions. Two integers k and l are multiplicatively independent if they don't have any powers in common. So this would exclude 4 and 8 because they both have 64 as a power. The other definition I'm going to say is that a subset of n to the d, any power of the natural numbers, is k-automatic if the base k representations of its elements form a regular language. Note that if we have, note that the elements of this might be tuples if we have d greater than 1. And in that case, what we can do is we can take an element, take a tuple, and then write each of the coordinates in base k, and then our characters will be tuples of the characters from the base k representations. And then if the set of resulting strings is recognizable by a finite automaton, the set is k-automatic. So, in 1969, what Cobham showed is that if we have two multiplicatively independent bases, k and l, the only way for a subset of n to be both k-automatic and l-automatic is if it is eventually periodic. And in 1977, Semenov figured out how this extends to the d-dimensional case, which is, in the same setup, a subset of n to the d is only both k-automatic and l-automatic if it is semi-linear. Semi-linearity, by the way, is equivalent to saying if the set is definable from, first-order definable from the addition function on the natural numbers. So it's a very neat characterization that I'm going to mention later. So, when we're talking about k-automatic sets, it's helpful to sort of have nice points to mark what, how tame or wild these can get. And so I'm going to define two predicates. One is k to the double struck n, and that simply is going to refer to the set of powers of k. The other thing I'm going to define is this function vk, and that takes some natural number n and maps it to the largest power of a that's a factor of n. This is if n is not equal to 0. If n equals 0, that would be undefined, so we just say it's 1. It doesn't really matter what we do in that case. And then, what Büchi proved in 1960, although his proof was slightly flawed. It wasn't, I believe, until Bruyère et al. In 1994 that it was formally patched. A subset of some power of the natural numbers is definable from addition and vk if and only if it is k-automatic. So you can look at this a couple different ways. You can see it as a k-automatic version of the characterization I mentioned a bit ago with semi-linear sets and being definable just from addition. You could also look at this as a sort of maximality of v sub k. We're saying that v sub k is a k-automatic set with enough internal associated structure that if we can define it, we can define anything else k-automatic. And then, on the other hand, we have sort of the dual result to this, which was shown by Bess in 1997, that if we have any k-automatic set that is not semi-linear, then the theory of addition with this set as a predicate will always be able to define k to the n. So k to the n has a sort of minimality. Anything else k-automatic will be able to define it. So, what we're going to focus on for the rest of this talk, really, is the notion of decidability of the first-order theory of a structure. And so the first case is one will note that if we have addition and vk in our structure, so this is essentially the structure of k-automatic sets, That structure does have a decidable theory. This is from the same 1960 Büchi paper that was a bit flawed and fixed later. I have an additional column here on the right, which is, does this structure contain a formula equivalent to the multiplication function? And the reason I have this here is because this is incompatible with decidability. If we define multiplication, we can define any arithmetical set, and hence any recursively enumerable set, and so decidability is completely out of the question. So obviously this does not define multiplication. But then if we look at the next row, we might ask, what if we have VK and VL in our structure? And what Viamer showed in 1992 is that then we do get a formula for multiplication. And so we obviously don't have a decidable theory. And then in the same 97 paper I mentioned earlier, Bess proved that it is sufficient to have Vk and L to the n, or equivalently from the minimality, any L-automatic set in our theory, because in that case we do still define multiplication. So the next natural question then, and this is a question that has been asked for quite some time, is what happens if we have k to the n and L to the n, or any k-automatic and any L-automatic set? Might that give us a decidable theory, or is it still undecidable? One other thing I want to note before we move on is that the results of Büchi and Bess are enough to prove the Cobham-Semenoff theorem. That is to say, if we have some L-automatic set that's not semilinear, from this table we know that it can't be k-automatic. Because if it were k-automatic, then adding it to our structure with Vk wouldn't change anything, and it would still have decidability, but Bess showed that it doesn't. So this is sort of an indirect proof of Cobham-Semenoff. So, let's fill in the last row, shall we? The result that I'm presenting today is that this structure with k to the n and L to the n still has an undecidable theory. One thing that's interesting to note is that we don't use the same proof technique where we define multiplication. In fact, although it's not written up formally enough for publication yet, I do have a proof that this structure does not define multiplication. So be on the lookout over the next, however much time I have in between writing my actual doctoral thesis. Be on the lookout for a paper proving that result as well, if you're interested. So let's formally state our result. First off, I'm going to restate Cobham-Semenoff, and that is, I'm going to say if we have a k-automatic and an L-automatic set that are not definable from addition, then the two sets aren't the same. Which is a strange way to phrase it, but the reason I bring this up is because it makes it clearer how our result is a strengthening of this. What we are saying is not only are these sets not the same, but they are sort of fundamentally incompatible in a sense that leads to undecidability if we adjoin both of them to our signature of our first-order theory. And as mentioned, due to Bess's result, it suffices to consider the case of k to the n and L to the n, so that's what the rest of this paper and talk focus on. Let me give you an example of what a sentence in this theory looks like, just to get some intuition. This is a rather complicated sentence, stating essentially that for all m, there is some n such that powers of k and powers of L greater than n must differ from each other by more than m. In other words, what this is saying is that as we consider larger powers of k and L, the gaps between them necessarily grow without bound. And what I say here is this is a corollary of Baker's theorem on linear forms. And Baker's theorem, I believe, if I'm remembering correctly, won Baker a Fields Medal. So this is sort of why it's easy to suspect that we get undecidability, because this is a highly non-trivial result that requires a lot of number-theoretic machinery, and if this theory were decidable, we could reduce proving this, famous theorem, or a corollary thereof, rather, to just running a computer program for enough time for it to give us an answer. So that's an intuitive reason to suspect undecidability. So let's talk a bit about some concepts used in the proof. We define this set S, and S is a relation between powers of k and powers of L. More specifically, we have this function lambda, which effectively rounds x down to the next power of k. So it's effectively the floor function, but with range powers of k. And then S is the set where we have a power of L such that when we round it down, subtract that power, and then round down again, we get a second power of k, and that second power of k is x. So what does this mean intuitively? What this means is that y is a power of L, and if we write it out in base k, the most significant digit is going to be a 1, the leading digit is a 1, and the second non-zero digit is in the x's place, where x is some power of k. So a concrete example, if it helps, if k is 2 and L is 3, 16, 81 will lie in S. Because if we look at the binary expansion of 81, the second non-zero bit is in the 16's place. And then the last thing we are defining on this slide is this function s of x, which effectively is just picking out one of the fibers of this relation. We're taking a power of k and asking which powers of L does it correspond to in this way. So the next thing I want to show you is this geometric diagram of how I sort of intuitively picture this, and that is in terms of this circle. Now, these two circles I've drawn are actually representing the same mathematical object. I'm just labeling different things. And the diagram was too cluttered if I put them on top of each other. So, what this is the circle of fractional parts of base k logarithms. And on the left, what I've done is I've partitioned it based on how the base k expansion of a number begins. So for k equals 2, here we have the things that start with 1, 1, 101, 1001, and so on, and these get smaller and smaller as they approach this sort of branch cut here. And then on the right, what I've done is I've labeled where on the circle various powers of L fall. And because the relationship of multiplying by L is an irrational rotation, these are going to sort of uniformly cover the circle in a way that is, I believe ergodic is a term that I can use, but in particular, the key here is that it's sufficiently generic that if we zoom in and look at small enough intervals, and we pick out certain powers of L, and look at when they cross those intervals, we can effectively get whatever we want in terms of a finite amount of data. And so here's the formal statement of that. Here what we have is we have some finite sequence, some finite word. Our alphabet is the integers 0 to r minus 1. Capital R is just arbitrary. And then what we're saying is there's some powers of k and powers of L such that the powers of k correspond nicely to the characters in our alphabet, and the powers of L that are within this S relation to each power of k correspond exactly to the indices within our string at which the corresponding character appears. So we can effectively encode any finite string this way. And in particular, all we need to know the starting and ending powers of k, and we need to know the starting and ending powers of L. So if you're familiar with some of Shillah's notion of tameness, this should ring some alarm bells and say, wow, this is not going to be tame. If you're not familiar with those, no worries, because our main concern is undecidability. So, not only can we encode finite strings using this method, we can use those to encode finite grids. It's not a perfect encoding, by which I mean there are some operations on a finite grid that you might want to do that you can't actually encode in this theory. But we have what we need. We can talk about cells, we can quantify over grids and over cells within those grids, and we can talk about what happens in the neighborhood of a given cell. And so what we can do is we can encode a Turing machine in terms of two corresponding grids. Here the rows are going to represent steps of execution, and the columns are going to represent slots on the tape of the Turing machine. The grid on the left is only going to have a value in one of its cells. And that value, the cell is going to be where our tape head is at that step, and the value is going to represent what state the automaton is in at that time. And then the grid on the right is very straightforward. It's the state of the tape at a given step. It's just which tape characters are where. And note that we can only encode a finite grid, which is fine, because if a Turing machine halts, it will only take a finite number of steps, and it will only use a finite number of cells. And so, by quantifying over these grids, we can take a Turing machine and convert all of the rules of its execution graph into a massive sentence saying there exists a grid that represents a halting run of this machine. And this is where we get undecidability, because of course, if we could decide this theory, we could effectively solve the halting problem. So, before we wrap up here, I do want to talk some about next steps. As I've mentioned earlier, I do have a result in preparation proving that this structure does not define multiplication. The proof is very model theoretic, but in case you are interested, again, be on the lookout for that. An interesting thing that I think would be good to explore in the future is, okay, so what happens, so we've proven this result for k to the n and l to the n, but if you look at the proof, it does rely on the fact that these are actually sets of powers. Like, let me give you an example, actually, of why that is. We want to be able to move from one column to the next column over. We want to be able to say, okay, this column is to the right of this column. And the columns here correspond to powers of k, so we need to be able to move to the next power of k. Of course, if k is a constant, that's as simple as a constant multiplication by k, but if we didn't have a set of powers, it wouldn't be a constant multiplication anymore. It would get a little bit trickier. And then we have similar issues with multiples, with powers of L. And so it opens up the question, okay, what if we replace one of them with something that is almost a set of powers, but not quite? Something that still grows exponentially, but isn't precisely a set of powers. And my go-to example for this is the set of Fibonacci numbers, because they grow exponentially, certainly, but they are not just a set of powers. They are the rounded powers of an irrational base. I believe there is a way to get the same proof to fall out from that case eventually, but I don't necessarily have that proof fully written up in any form yet. And then the other question is, well, okay, forget about exponential growth, what about other kinds of growth, right? How far does this go? What if we have powers of 2 and factorials? Is it, do we still get undecidability from weird number theoretic properties, or is it possible that those sets are enough unlike each other, in terms of, in some way that they don't really interfere with each other from a decidability perspective? And there are a lot of open questions here. There definitely are. That is largely the conclusion of the talk. I do have 2 pages of references, so I'm going to show you this page for several seconds in case you want to write any of these authors and titles down. And then here is the second page of my references. If you have any questions, I of course can't answer them in a video recording, but of course I'll be there in Rome. We will have poster sessions, we will have in-person presentations, so you'll have opportunities to talk to me then. Apart from that, that is the conclusion of the talk, and thank you very much.